All right, guys, welcome to today's lesson on the process of titration. It says, one of these days, Harris, I'm going to fire your ass. Donkey. Here's what titration is, guys. It's a process. We use this funky glassware here called a burette. I'll show you. If we were in class, you guys would be using this. In this technique, a known concentration of base or acid is slowly added to a solution of acid or base. So you guys, here's essentially the process of titration. So let's say I knew this was a sodium hydroxide. It was in my sodium hydroxide, you guys know, as a base, right? It was in my stock room, but let's say it wasn't labeled correctly and it didn't have the concentration. This is pretty much useless to me. I need to know not only the identity of the solution, but I need to know the concentration. Well, rather than just tossing this, I can use the process of titration by which I can find what the concentration of this sodium hydroxide is. And I titrate it with a known concentration of an acid. Okay, so here's how it works. So I have my base. Let's say I have this, so this is sodium hydroxide. Let's say I have 50 milliliters, okay? So that would be the volume of my base. Got 50 milliliters, okay? So my base is NaOH, and then I'm gonna titrate it with, let's say, hydrochloric acid, okay? So I got 50 milliliters of it. I don't know the concentration. Let me make sure you guys are able to see that. I don't know the concentration of my base, okay? But I have an acid, let's say my acid here, let's say my acid here is 1 molar. So I have 1 molar hydrochloric acid, okay? So now here's what I'm gonna do. What I'm gonna do is, I'm going to, of my base, and you guys remember what really makes it a base, you think hydroxide ions, OH minus ions, and what makes really this an acid is the higher concentration of H plus ions. So you guys can imagine when I add the acid to the base, what's gonna happen is the typical neutralization reaction. You guys right? The H plus from the acid combines with the OH minus from the base, and I form water. What I want to do is I want to reach, and that's called the equivalence point, is when you've added just as much H plus ions as there is OH minus ions. We might say it's become neutralized. But you guys could imagine, what's the problem? Let's say if I needed to reach that neutralization or the equivalence point, when I add the acid to the base, what's the point? Ultimately it's going to be neutralized, but what's the problem? When you guys agree, I'm not going to know when I've reached that point, right? Because when you guys agree, if I keep adding acid, there's going to come a point in which I'm going to add more H plus, that the H plus ions that I'm adding are going to exceed the OH minus ions, and then that solution, which was a base, now becomes an acid. So how do we alleviate that problem? We use what's called an indicator. So in this case, I'm going to use bromothymol blue, and an indicator is really a substance that simply changes color depending on what pH environment it's in. So, for example, I have bromothymol blue. I'm going to put it in my base. And then you guys see, there's a reason why it's called bromothymol blue. Well, duh, because it's blue. So bromothymol blue gives off a blue color when it's in the presence of a base, okay? So now, I have my indicator. So now I'm going to proceed to add my acid slowly to my base, okay? So I add some acid here, okay? And you see that the solution is still blue. So what does that tell you about your solution? Wouldn't that tell you it's still a base? And why is it a base? Because the OH minus ions still exceed the H plus ions. So that means I got to continue to add more acid. So I'm doing it, and then I'm swirling as I'm going. And we see it's still blue, indicating it's still a base. The hydroxide ions exceed the H plus ions. Okay. So I'm still adding my acid, and I think you guys are kind of starting to see what's happening. Oh, and then all of a sudden you see it is yellow. Bromothymol blue is an indicator which is yellow in an acidic environment. So I reached the point, and you guys see why the whole difference, the whole thing is here, we typically use a burette here, and the whole reason is so that we can add that slowly. You see how I was doing it kind of crudely? Because you guys can imagine at this point, this is actually probably more acidic, because I probably overshot and added more H plus than the OH minus, so I went over the equivalence point. Using a burette would allow you to add it very slowly so you can reach the exact point at which the H plus ions is equal to the OH minus ions. So now, let's see what we've got. So basically, now what I'm going to do is, then I would measure, and we could use a burette, and you can see how much acid did you add to the base. And so in this case, let's say, in order to reach the equivalence point, let's say I added 25 milliliters. I added 25 milliliters of my acid. Okay. So now, you guys looking, I have the molarity of my acid and I have the volume of the acid. What could I figure out? Well, you guys should remember from our molarity equation, molarity is moles per liter. If I know the molarity and the volume, I can get the moles by multiplying both sides by liters. So I'll go liters, how many liters? That's 0.025 liters times the molarity, which is 1. And you guys know molarity means moles per liter, and that's why the liters canceled out. And so what did I figure out? I added into that solution 0.025 moles of H+. That is the amount of H+ ions that I added to this solution right here. So if that is the equivalence point, right, where the H+ ion concentration equals the OH- ion concentration, then shouldn't that equal 0.25? That must mean there must have been in my original, you guys right, in my original base, there must have been 0.025 moles of OH-, right? Because that's how much H+ ions I added to reach the equivalence point of the hydroxide ions that were there. So I know it has 0.25 moles of OH-, and what else did I know about my base? I started with 50 milliliters. So now in this case, I know the moles and I know the volume. What could I figure out? Right? Once again, it's molarity is moles over liter. I can figure out the molarity. So there was 0.25 moles of hydroxide ions. You guys, wouldn't you guys agree? There's for every one NaOH, there's one hydroxide. So that would be 0.25 moles of hydroxide, sodium hydroxide for, and I have 50 milliliters, which is 0.05 liters. I'm sorry, I didn't do that right. I'm sorry. That's where I messed up. I'm sorry. 0.025. I'm sorry, 0.025, my bad guys. 0.025. So if I go 0.025 over 0.05, what am I going to get? 0.5 molar. Sorry guys. I figured out I have 0.5 molar. So that's half a molar. So then you guys on my solution, what I could do is, right, let's say I just took a sample of that sodium hydroxide, let's say there was a big bottle. Now I could label it properly and I would put 0.5 molar NaOH. So you guys, hopefully you guys are kind of seeing titration is the process by which you add an acid or base to another one in order to determine its unknown concentration. So you could use a pH meter. You guys see in this case we used an indicator because we have to be able to determine. Now if you used a pH meter, I would have just put a pH probe in that solution and then waited until it hit pH 7, which indicates the neutral point. And that's the equivalence point is where you have equal amount of H+ and OH- ions. Okay, so what we observed here, guys, was the titration of a strong acid with a strong base. And so what you're going to find is, and we're going to look at a little animation. So let's say, now this is going to be a little different. Now, let's say we did the reverse, okay? So let's say we had an acid. So let's say I take the pH of an acid, and as you guys would expect, it's really low, right? It's pH 1. Then I'm going to proceed to add a base to the acid, and what do you guys see? You see the pH begins to slowly move up until the point at which, and we're going to show you guys why the pHs reflect this, until you're starting to approach the equivalence point. Then you're going to notice the pH value is going to immediately shoot up, and then it's going to stabilize. What you guys will realize when you titrate a strong acid with a strong base, the equivalence point, as you guys might expect, is at pH 7. Why do you guys expect that? Because the H+ and the OH- ions are in equal amounts. They neutralize, form water, therefore, and there's no other ions that can affect the pH, and therefore you would expect the pH to be at 7. At the equivalent point, the moles of acid equals the moles of base. That's what we've been saying here. And the solution contains only water and the salt from the cation of the base and the anion of the acid. Like for example, in this case, you guys see what they're saying here. If it's HCl and NaOH, right? When the H+ and the OH- ions are equal, what else do I have left? I just have sodium ions and chloride ions. neither of which affect the pH, and therefore you expect the pH to be at 7. You're going to get a better idea of this on the next animation. I'm having trouble with this. No. One sec here, guys. Let me try to figure this out. Stick with me, guys. I'm still here. Sorry. One sec, guys. I'm gonna go back to the video or the animation. Okay, you know what? We're gonna have to skip that, unfortunately. So you guys, let me explain what's going on with just this. So you guys think about it. Initially, let's say we have hydrochloric acid, right? And you guys see the presence of the H plus ions. That's what's making this have a very low pH value. Okay. So then, as we begin to add NaOH, you guys think about it. If we add NaOH, wouldn't you guys agree the hydroxide ions will combine with the H plus ions? So as I begin to add OH minus ions, they're going to combine with the H plus ions, and so it's going to reduce the amount of H plus ions in solution, right? And so what's going to happen is you're going to find that the pH value is still, it's going to be going up slightly. But why is it still very low? Because we still have a lot of H plus ions. And then as we continue to add OH minus ions, it continues to rise up. And now you can see, right, there's still H plus ions present, and therefore it's still a low pH. But then eventually we're going to add just enough OH minus where all of the OH minus or all of the H plus ions are used up. So you guys, at this point, we have sodium ions and the chloride ions from the hydrochloric acid, right? That's what that's showing. So at this point, all you have is sodium chloride in water because we added enough OH minus to fully react with all the H plus. And so immediately at that point, once you add that last drop, the pH is immediately going to shoot up to pH 7, and right, once again, it's pH 7 because at this point it's neutral. But then as I proceed to continue to add more OH ions, now you guys are going to see, now in solution you don't just have sodium ions and chloride ions, you also have OH minus, now you have OH minus ions present because you added more, and as expected, the pH is going to be shooting up because now you have a higher and higher concentration of OH minus, and then it will begin to stabilize again at a high pH value. Okay, now look at this. What if we titrate a weak acid with a strong base? Okay, so now you guys got to think about this. Let's look at that. Let's look at that scenario here. Okay, so now we have a weak acid. So think about a weak acid, right? Remember, it only partially dissociates, and it's going to form. It's going to give up an H plus to water, and then you have its conjugate base. Okay, And you guys remember, the conjugate base here is stronger than the weak acid here. Remember, this is more heavily favored, so this has a strong attraction for H plus ions. So we have our weak acid, and as you would expect, if you get the pH of your weak acid, it's going to be a pH lower than 7. So let's say it starts at 3, okay? And why is that? Because you have the presence of the H plus ions, okay? But now all of a sudden we start adding some sodium hydroxide, okay? And as expected, what happens? You're going to see the pH goes up slowly, right? As we add a base, let's say we're adding NaOH, because once again, now you're introducing OH minus ions, and what's going to happen? Those are going to combine with H plus ions to form water. So what are we doing? We're reducing the amount of H plus ions in solution, and therefore it's becoming less acidic, okay? So it's going up. But why is it still an acid? Because we still have the presence of these, we still have more H plus ions, okay? But now, eventually you're going to reach the equivalence point. And you remember, that's the point at which we've added just enough OH minus as the H plus that are present. So all of the H plus ions and OH minus ions have combined to form water. But you'll notice, at the equivalence point here, notice it's at a pH of about like 8.5, 8.5. Why is the pH not at 7? Because you think about it, even when all the H plus ions have been used up, what is still present? It's the conjugate base of a weak acid. So it's the presence of this conjugate base which makes the pH basic even at the equivalence point where you've added just enough OH minus ions to fully react with the H plus ion that were present, okay? So recognize that, guys. The pH level is going to be higher than 7 when you titrate a weak acid with a strong base, because even when the weak acid is fully titrated, you have the presence of its conjugate base, which makes it basic. Okay? So at the equivalence point, in this case, the pH is greater than 7. So the question is, if you were going to titrate a weak acid with a strong base, which kind of indicator would you use? You guys remember I said different indicators change colors at different pH values. So I know it's kind of hard to see on this chart, but here, this goes from, phenolphthalein goes from a clear to a purple here, and methyl red goes from a yellow to a red. Well, understanding that the titration of a weak acid with a strong base reaches its equivalence point at a pH higher than 7, you should choose phenolphthalein, because phenolphthalein has its color change in the 8 to 9 range, and therefore you would recognize, as long as that equivalence point falls within the range of that indicator, that would be an appropriate indicator to be able to identify the equivalence point, okay? Last kind of titration, you guys think if there's a titration of a weak acid with a strong base, you guys could probably guess, there could also be the titration of a weak base with a strong acid, okay? So, in this case, what we're doing here is, we're starting with a base, and as you would expect, the pH of a base is greater than 7, and as we add, so we have a weak base, just imagine like ammonia, okay, that's our typical weak base, and you guys see why it would be basic, because ammonia, at least partially, will get a proton, an H plus ion from water forming OH minus ions, and therefore that would explain why it has a basic pH. Now what we're going to do is add hydrochloric acid. And you guys can imagine, as you add hydrochloric acid, now you're introducing H plus ions. Obviously the H plus ions are going to combine with the OH minus ions to form water, okay? So what we're doing is we're reducing the amount of OH minus ions that are present, therefore we're making it less basic, more acidic, so the pH is going down. Well, and it'll keep going down slowly, gradually, until the point at which you're approaching the equivalence point. So, right, when we get close to where we've added just enough H plus ions to fully react with all the OH minus ions present, immediately the pH is going to shoot down dramatically. And the equivalence point is the point at which, right, the H plus ions equals the amount of OH minus ions present, okay? What you'll notice about this, the equivalence point, this is at a pH, look, it's at about around 5 or so, 5.5. That's a pH less than 7. Once again, why is that? Because if I add hydrochloric acid to this weak basic solution, so I got my H plus with my OH minus, right? Let's say all of these get used up now, right? So those all come out as water. What do I have left? I have ammonium ions, NH4 plus ions, and I have chloride ions. Now the chloride ions don't affect the pH because that's the conjugate base of a strong acid, so it's not going to have any effect. But this is the conjugate acid of a weak base. So even when this base has fully been titrated and we reach the equivalence point, and we've reacted all the OH minus ions, what's still present is the conjugate acid. So when you titrate a weak base with a strong acid, at the equivalence point, you're going to have present the conjugate acid of the weak base. You guys remember conjugate acid-base pairs only differ by hydrogen. And so the presence of that conjugate acid is going to make your solution acidic, right? Because this has the potential to give up H plus ions, right? So it's going to make your solution acidic even at the equivalence point. And we can see that that's characteristic here. And then, so in this case, if I'm titrating a weak base with a strong acid, anticipating that the equivalence point is going to be lower than pH 7, I'm going to use an indicator, because you guys remember the whole point was we have to use an indicator where the color changes, where the equivalence point is expected to be in the range of the color change, so we know where to identify that equivalence point. So in this case, what would I use? I would use methyl red as an indicator, knowing that its color changes in the range between like 4 and 6, which is under the 7, as I would expect for this titration. And we talked about that. And I think that might be it. The pH at that point is less than 7. All right, guys, good stuff. Thanks for hanging in with me, even with that glitch there, with the technical difficulty. Until next time.